Hey everyone, welcome back. So this example will be pretty much the third for this chapter, right? The first example, we didn't have any rotation at all. The second example, I did a variety of ways. We had to incorporate some torques, right? Because we may have had some rotation. However, all of the r and f vectors were perpendicular to each other. In this example, we will have some angles, okay? We have an angle theta right there, in fact. So our second law equations will be a little bit more complicated, but not too much more, right? So let's walk ourselves through it here. All right. So the picture, as shown, is we have this beam, right? This rigid metal beam of some uniform mass density, such that its center of mass is at, well, the center of it, okay? So it's connected to the wall by this hinge, and it's able to freely rotate about that hinge, right? So that may be a natural axis of rotation for us later on. From the top point of that beam, it's connected to the wall via a cable of length B, okay? Also hanging down from the top end is a mass of, well, mass capital M, connected by a rope, okay? So let's take a look at the forces on that beam, right? In order to write our free body diagram. In order to do that, though, we have to really consider what the system is, right? In this case, the system really is the beam. That's it, okay? You can incorporate, or you can say the system includes the mass also, sure. But we're really talking about what forces are at play that may or may not cause rotation on that beam. Okay, that's our system. So let's draw the free body diagram over here to the right. I'm going to include the wall, even though that's not exactly part of the system, but that's okay. It's okay for this free body diagram purpose. Okay, so here's the strut, something like that. All right, so all of the forces on it, well, there's its weight, right? So let's just start there. Its weight from the, whoops, actually, let's do that at a slightly greater angle. There we go. Okay, going back to regular font here. Its center of mass, right? It has its own weight downwards, lowercase mg, right? That would torque it clockwise. Another force is the force of the cable, right? From the top, pulling it towards the wall. And so that cable force is actually in part A. That's the tension that we're trying to find, because that horizontal cable is under some tension. Now, that's what we're trying to find, right? That tension there. Well, that's really the same as the tension of the cable on the wall at that connection point. However, this connection point is not necessarily related or not directly involved in the beam. So we do not incorporate that force there, okay? Yes, those two are the same tensions in magnitude, right? But we're only worried about the force on the beam. In that case, it's this tension here. So that's two forces so far. Next, we have the rope pulling down on the end of that beam, right? So that's another tension. So if you want, let's write that on our actual image here. I'm going to call that T prime, okay? It's not the same as the tension in the cable, okay? So this T prime, that T prime is the force on the end of the beam downwards. But because this is an ideal string, or at least can be considered ideal, that's the same as the force of the rope pulling up on that mass, capital M. And if you wanted to try and write this as kind of a mini system, right? Well, T prime going up, that's counteracting the weight of that mass. Rather, the weight of that block. That's a better sentence there. And so from here, we can see that really T prime is just capital MG, right? So in our free body diagram, from the end, we can really just write capital MG. Okay? Also, another way to reason through that is that T prime, there and there, are both internal forces. So if we think of the strut, the cable, and block all as one system, well, now this rope here is inside that system, right? It's inside our frame of reference. In other words, those are internal forces. The only external force is the gravitational force there, pulling down on that block. And so that's the force we use as the external force acting on the beam. Okay? So there's 3 forces so far, and now it's the force of the hinge, or rather, in part B, the force of the beam, the force on the beam from the hinge, right? So that actually acts up the beam like that, which means there's 2 components. One horizontally, right, perpendicular to the wall. It's this component here that prevents the beam from falling into the wall. Okay? And then there's also a force of the hinge on the beam in the upwards direction, right? Parallel to the wall, upwards. That's preventing the beam from sliding down. Okay? So, on our free body diagram, we can write it like such. I'll call that Fx, and this force upwards, Fy. Okay? And those are all the forces, right? 5 force components, if you will. So we need to choose an axis for our equation. So let's just do the normal xy. And remember, positive torque is counterclockwise. Okay, so let me translate this free body diagram to the next page. Nope. Let's try it again. No. I just want this guy. Let's see. I need to move that up a little bit. Now let's try it again. There we go. Okay. Now we're back in business. All right. So using this free body diagram, we can write out our equations for the forces and the torques. In the x direction, the positive force, right, the only force in the plus direction, well, is Fx. The only force in the negative x direction is the tension in the cable. And because nothing is moving, this being chapter 12, it's equal to 0. In the y direction, the positive force, or rather the only force that's positive, is Fy. And the 2 weights are negative. We have the weight of the beam itself and the weight of that hanging block. And that's equal to 0. All right? And so, time to do the torques. So, as you saw in last example, because we're in static equilibrium and nothing is actually rotating about an actual axis, that means that you have the freedom to choose your own axis, right? To write the equations, write this sum of torques equations about whatever point you want, right? I suggest doing it about, at least in this case, the natural axis of rotation, being the hinge, okay? So there's 2 reasons for that. First is that it's a natural axis of rotation, right? If, say, that cable was cut, that means those 2 weights are torquing the beam clockwise, right? Downwards, and it would actually rotate about this hinge that it's connected to. The other reason is that if you choose the hinge here, there are two forces, Fy and Fx, that are acting from that exact point. That means there are no torques, right? They do no torque because their r vector is 0. So you basically eliminate 2 out of the 5 potential torque terms. Say that 10 times fast. So that leaves us, if I choose the hinge, which I will, 3 forces that create a torque, right? So let's write them out. There we go. That's our hinge. That's our axis. All right, remembering counterclockwise direction is a positive torque. Now it gets a little bit tricky. Okay? So stay with me here. I'm going to, let me change colors here. The actual beam from the point of rotation, let's go up to the tension because that would rotate it and cause a positive torque. You can't really see that. You can do torque two ways, right? One of two ways. The radius vector, right, the r vector, is always pointing from the axis to where the force is applied. So for the tension up top, that's the radius vector there, right? That's actually r. Now, you can do that, right? That means if that's the radius vector, torque, remember, is, I'll just do it down here. Torque, remember, is R cross F, okay? That's equal to the magnitude of both times sine of the angle in between. And I really shouldn't write theta here, because what does the problem say theta is? The problem says theta is right here, right? The angle in between the horizontal cable and the beam. So we actually need to mark that. That's theta. The magnitude of torque is RF times the sine of the angle in between those two forces. Well, guess what? That's not theta, that's this angle here, right? That's another angle, right? 180 minus theta. If you want to call that a different angle, you can. I'll call it phi, right? So this is one way. You could figure out that angle, calculate the magnitudes, and do it that way. The other angle, or the other way to do it, is to find one of the perpendicular components to the other vector. What do I mean? Well, let's go down below. Okay, so let's draw that, let's draw that beam again, okay? Here's our hinge, right there. Hinge. Now, this beam, by the way, I'll say is of length L. What I haven't specified yet is that actually we have some lengths here, right? This is actually of length, what does the problem say? B. The cable is of length B, and vertically, it's of length A. Oops. So that's B, and then this here is of length A. So the beam itself is of length L, right? You could find that if you wanted to. But what do I mean by the perpendicular components? Well, the tension here, right? The tension, if I were to translate that across, let me put that in red. The tension is acting from the end, right, I'm going to actually go across to where it's directly above the hinge. I'm just going to move that over, okay? Same vector now. So then what is this vector? What's that in green? If that's theta, that means this is theta as well. In green here, that means this is L sine of theta, right? Because the beam itself is of length L. And L sine theta and T are perpendicular. So now in our torque equation, our R cross F can be written as, well, our R perpendicular. L sine theta now, right? That's the first vector. The second vector is the force, which is the tension, and sine of the angle in between these now, well, that's sine of 90. That's just 1. Okay, that is 1. So this L sine theta is the R perpendicular vector. Okay, and the tension is the force. So you can do it either of these two ways, right? Let's write the second torque term. So now we have torques from the two weights, mg and mg, right there. So now let's come up with the R perpendicular for this mg down here, right? Let's do that. Let's see, I'm going to keep the forces in red. Let me keep the forces in red here. So from the center, that's the actual weight. If I translate that down here, lowercase mg, all right? Now in green, we're going from the hinge, or from the point of rotation, to where that force is applied, right there. And so now, well, what's that vector in green? That is L over 2 cosine theta. All right, that's the R perpendicular for this torque. And the angle in between these two now, right, in green and in red, that's 90 again. So we have a similar thing to above. This torque is negative because the weight, right here, this force would rotate it clockwise. Okay, so we have L over 2 cosine theta. Whoops, that's in green. It doesn't matter. L over 2 cosine theta times the tension, the force, which is lowercase mg. All right? And a very similar thing for the weight of the block. Right? That force is applied there, but I'm just going to translate it down, capital Mg, and now in green, that simply goes all the way over, and now that vector here, that whole distance is now L cosine theta, all right? And so we have, for the torque, is negative L cosine theta, capital Mg, and this all equals 0. Okay? So, we have 3 second law equations. What do we want to find? If you remember back to the very beginning, we should find the tension in the cable and then the magnitude of the force on the beam from the hinge. Okay, so can we find the tension straight away? Well, tension's equal to Fx. We don't know what Fx is necessarily, but we can use the torque equation to find tension because we know both masses, we know the angle, or at least we can find the angle, and look what happens to the length of the beam. L cancels out. Okay, so let me rewrite this torque equation. We have T sine theta minus 1/2 mg cosine theta minus capital Mg cosine theta all equals 0. I'll put 0 over here. Okay. All right. Oh, by the way, on these last two torque terms, I didn't write sine 90. That was implied. Okay. So we need to figure out what theta is. Theta. Well, theta, again, is that angle there or that angle there. Well, since we know both A and B, right, we know both of those because the problem tells us A and B. Theta, actually I have more room here. Theta equals inverse tangent of opposite over adjacent. So that means it's A over B. Okay? And this should be about 37.2 degrees. Okay? So 37.2 degrees for theta. We know the masses, we know G. We can solve for tension. So 1/2 mg cosine theta plus capital Mg cosine theta all over sine theta should give us, I'll say, approximately 6,100 newtons for the tension. Okay, approximately, right? All right, so I'm going to skip to the next slide to find the magnitude of F, all right? We know, whoops, let's do, those were my notes. Let's skip 2 slides ahead now. We know that tension equals Fx. So we know that straight away. That's nice. Fy was equal to, right here, the sum of both weights. All right, so this works out to be roughly 7,900, right? 7,920 if you want to be a little more exact. And then finding the magnitude of F, we just use Pythagorean theorem. And this should be about, I lost it. Let me check it here. Oh, I'm sorry. 5052. Sorry, Fy should be 5052. 5,052. And then the magnitude of F overall should be about 7,920 newtons. All right. So again, the important part of this problem, aside from, everything, is being able to write out the torque equation, right, from the free body diagram. That means choosing an axis, right? I chose this point because 1, it was a natural point of rotation, and 2, it negated 2 torques, right? So we only had 3 out of the potential 5 torque terms, all right? Again, you could have chosen this point, or you could have chosen this point, really, but it would have been a little more of a headache, okay? And then I found the terms, right, meaning T sine theta and 1/2 mg cosine, etc., because I found that the perpendicular component to the force, in this case, was L sine theta in these cases were, either 1/2 L or L cosine theta. And then that allowed me to make, since those are perpendicular, we had R perpendicular times T, times the force, and then sine of 90 was just 1. And so this whole term reduced down to LT sine theta, and then the L's canceled out. Okay, so this is kind of the crux of static equilibrium problems, right? Choosing your axis and being able to write down the torque equations. After that, again, it's just algebra. Okay, so this is the important part. This is the physics right there. So with that, again, our final answer was 7,900 for the magnitude of F, and then the tension was 6,100. All right, thanks for watching.